Right now, while you are watching this video, in the middle of one of the harshest deserts on Earth, a drilling tower the height of a 24-story building is operating without pause. It stands in the heart of the Taklamakan Desert in northwestern China, where summer heat can climb beyond 50 degrees Celsius, and winter drops below -30. There are no cities nearby, no highways, no comfort, only endless dunes and burning sand stretching to the horizon. And this machine keeps grinding downward, meter by meter, forcing its way into layers of rock few humans have ever reached. The well is called Shendi Take 1, and its planned depth was 11,100 meters. That is deeper than commercial jets fly. Deeper than Mount Everest would reach if you turned it upside down and drove it into the earth. China decided to create one of the deepest holes ever made on this planet. And the question asked around the world was simple. Why? Why spend billions to punch a narrow shaft into stone in the middle of nowhere? The answer, as usual, is far more complex and far more fascinating than it first appears. Today, we are going to uncover what China was searching for nearly 11 kilometers below the surface, why some scientists see this as revolutionary while others see danger, and how this single hole could connect to the future of all civilization. Because the story of ultra-deep drilling is not just engineering. It is ambition, failure, mystery, politics, and science woven so tightly together that sometimes they become impossible to separate. To understand why China is drilling downward, you first need to understand what lies beneath us. And this is where the story becomes truly strange. Humanity has sent machines to Mars. We have photographed a black hole 55 million light-years away. Yet we still barely know what exists under our own feet. The distance from Earth's surface to the center of the core is roughly 6,370 kilometers. The deepest borehole ever drilled, the Kola Superdeep in Russia, reached 12,262 meters. That is about 0.2% of the journey to the center. We have barely scratched the surface. If Earth were an apple, we have not even pierced the skin. Everything we know about the mantle, the outer core, and the inner core comes mostly from indirect evidence. Scientists study how seismic waves from earthquakes move through the planet, then use changes in speed and direction to build models. Imagine trying to learn what is inside a watermelon without cutting it open, only tapping the shell and listening to the sound. It works, but only partially. Direct access is different. Pulling up real rock from 10 kilometers deep, placing it on a laboratory table, and studying it directly is priceless. And that is exactly why China went underground. But China was not the first nation to try. The race for depth began during the Cold War, and it was almost as dramatic as the race for space. In 1961, only weeks after Yuri Gagarin flew into orbit, the United States launched Project Mohole. The goal was to drill through the ocean floor near Mexico and reach the boundary between Earth's crust and mantle, the Mohorovicic discontinuity. The idea was brilliant. Oceanic crust is thinner than continental crust, around 5 to 7 kilometers instead of dozens. Reaching the mantle there seemed easier. Early tests recovered rock samples from beneath the seabed and made global headlines. But the project drowned in bureaucracy, cost overruns, and political conflict. By 1966, Congress ended the funding, and Mohole died before reaching its target. The Soviet Union watched the collapse with thinly hidden satisfaction. Then, in 1970, almost exactly on the centenary of Vladimir Lenin's birth, Soviet engineers began drilling on the Kola Peninsula. The site was chosen carefully. It sat on the Baltic Shield, one of Earth's oldest crustal regions, where rocks billions of years old rise near the surface. Scientists believed that somewhere between 10 and 15 kilometers down, they might finally reach the mantle. The first years went smoothly. By 1979, the Kola well had passed the American Bertha Rogers record in Oklahoma and moved beyond 9.5 kilometers. By 1983, it crossed 12 kilometers, and Soviet geologists celebrated. In the summer of 1984, during an International Geology Congress in Moscow, officials announced a depth of 12,066 meters. Delegates were flown north, shown the drilling site, and handed cylindrical rock cores lifted from unimaginable depths. Then the nightmare began. In September 1984, after drilling resumed following the Congress, disaster struck almost immediately. During the first descent of the tool string, a 5-kilometer section of drill pipe jammed and snapped, disappearing forever inside the hole. Years of work were trapped underground in seconds. Engineers had no choice but to begin again from around 7 kilometers, steering a new path around the lost equipment. By 1990, they managed to reach 12,262 meters. That became the all-time record, and it still stands today. But the greatest discoveries of Kola were not about depth. They were about what the Earth revealed once humans finally forced their way inside. Before drilling began, geophysicists were confident that granite layers would give way to basalt at roughly 7 kilometers. Seismic readings strongly suggested it. But when the drill arrived there, the expected basalt never appeared. Instead, the well continued through granite and gneiss, only hotter, fractured, and increasingly deformed. The boundary scientists trusted for decades simply was not there. Models that looked certain turned out to be wrong. Then came the temperature shock. Predictions estimated rock temperatures near 100 degrees Celsius at 12 kilometers. Real instruments measured around 180 degrees Celsius. That meant heat flow beneath the Kola Peninsula was far more intense than expected, and the mantle boundary was either much deeper than hoped, or organized in ways textbooks failed to describe. But perhaps the most surprising discovery was water. At depths where rock was supposed to be dry, compressed, and sealed solid by crushing pressure, the borehole encountered hot mineral-rich fluids. Water existed throughout cracks and pores at levels where nobody believed it could survive. It could not have seeped downward from the surface under such pressure. That meant it had been trapped there since the rocks first formed billions of years ago. Kola proved that Earth's crust was not a dry stone shell. It was more like a vast sponge carrying fluids through hidden fractures. Those fluids help move heat, shape minerals, and influence tectonic forces. In other words, they help drive the planet itself. There were mineral surprises, too. At depths beyond 9.5 kilometers, the borehole found rock containing unusually high gold concentrations, up to 50 grams per ton. Industrial mining can be profitable at only a fraction of that. The implications were obvious. Deep Earth might hold riches nobody had imagined. Then science collided with myth. In 1989, a Finnish newspaper published an April Fool's story claiming Soviet scientists had lowered microphones into the hole and recorded terrifying screams from below, sounds they interpreted as hell itself. An American television network repeated it as fact, and the story exploded worldwide. Soon, the legend mutated. Some said demonic creatures burst from the shaft. Others claimed workers refused to go underground. Some insisted every new kilometer brought fresh disaster to the Soviet Union. When drilling approached 13 kilometers, believers even linked it to the collapse of the USSR. David Guberman, who led the project for years, later joked that when someone at a UNESCO meeting asked what exactly they had uncovered down there, he hardly knew how to answer. On one hand, nonsense. On the other, strange noises had indeed been detected. And in 1995, an unexplained explosion occurred at the site. The true cause was never fully established. Of course, no screams from hell were ever recorded. Borehole acoustic tools do not capture voices from the underworld. They measure reflected waves generated by the instruments themselves. But legend proved stronger than fact. To this day, Kola remains one of the most mythologized scientific sites on Earth. And then, roughly 30 years after Kola fell silent, China decided to begin again, this time with different motives, different technology, and far greater industrial power. On May 30th, 2023, in the Taklamakan Desert within the Tarim Basin, a drilling platform built specifically for ultra-deep work began operations. It became the first fully automated rig of its kind, standing 72 meters tall with a top drive lifting capacity of 900 tons. On March 4th, 2024, the well crossed the 10,000-meter mark, an achievement broadcast on state television. By February 2025, drilling was completed at 10,910 meters, the deepest vertical well in Asia and second deepest in the world after Kola. The entire operation took a little over 580 days, yet the final 910 meters alone required nearly 300 of them. One engineer compared drilling at that depth to driving a heavy truck across two thin steel cables. So why did China go this deep? The first answer is the obvious one: oil and gas. The Tarim Basin is China's largest region of deeply buried hydrocarbons. More than 60% of the nation's ultra-deep oil and gas reserves are believed to lie here, hidden beneath sedimentary layers reaching 10 kilometers or more. China is the world's second largest oil consumer after the United States and one of the biggest importers on Earth. Dependence on foreign energy, from the Middle East, from Russia, from distant shipping lanes, is a strategic weakness Beijing cannot ignore. Every barrel produced at home is one less barrel that must be bought abroad. Previous exploration wells had already suggested that oil and gas do exist below 8 kilometers in the Tarim Basin. Shendi. Take One was designed to answer a far larger question. Are there commercially usable reserves at 10 kilometers and deeper? If the answer is yes, China opens a new energy frontier that almost no other nation has reached. But oil is only the first layer of the answer. The second is geothermal power. At depths near 10 kilometers, rock temperatures can exceed 200 degrees Celsius. Beneath every square kilometer of land sits an enormous reservoir of heat. If engineers can learn to inject cold water downward and recover superheated steam at the surface, humanity gains a near-limitless energy source that does not depend on sunlight, wind, seasons, or politics. A solar panel goes dark at night. A wind turbine can stand motionless in calm air. But the heat of the earth does not switch off. It has been burning for billions of years, and it will continue long after modern civilizations are gone. According to estimates from the International Energy Agency, geothermal resources between 5 and 10 kilometers deep contain energy tens of thousands of times greater than all known oil and gas reserves combined. The problem is simple: reaching it. That is why ultra-deep drilling matters so much. In November 2024, China completed its deepest geothermal well, Fushenri G1, on Hainan Island, reaching 5,200 meters through granite, around 250 million years old. It is part of a much wider push to harvest deep planetary heat and lessons learned from Shendi. Take One directly support that mission. Then comes the third layer, pure science. And this may be the most valuable reward of all, Shendi. Take One passed through 13 continental strata and reached rocks from the Cretaceous period, formed roughly 66 to 145 million years ago, the age of dinosaurs. Every meter of core brought to the surface is a page torn from Earth's hidden archive. Mineral composition, isotope signatures, microscopic traces of ancient fluids sealed inside pores. These details allow scientists to reconstruct tectonic shifts, climate transitions, and even environmental conditions linked to the evolution of life. No satellite can do that. No surface survey can do that. Only direct access can. China has placed this project inside a broader national strategy, sometimes described as the 4 depths: deep space, deep ocean, deep earth, and deep blue development. It links lunar probes, submersibles, polar research, and underground engineering into one narrative of technological rise. Chinese scientists openly compare the symbolic value of this well to the landing of the Chang'e lunar probes or the dives of deep-sea submersibles. For them, this is not just a borehole, it is a statement. But there is a fourth layer rarely discussed in public, even though it may be the most urgent. China sits within one of the world's most seismically active regions. The 2008 Sichuan earthquake killed nearly 70,000 people. It ruptured at depths geologists still understood poorly. Direct access to deep rock can help measure stress in the crust, monitor temperatures, track fluid pressures inside fractures, and place instruments capable of detecting warning signals before disaster reaches the surface. This is not fantasy. Japan already uses advanced monitoring systems, though generally at shallower levels. China wants something deeper and broader, a subsurface early warning network built on real measurements rather than theory. To do that, it needs to know what truly happens 10 kilometers down. Naturally, the internet had other ideas. Conspiracy theories appeared immediately. Some claimed China was searching for buried bases of an ancient civilization. Others insisted the well was part of a geophysical weapon capable of triggering earthquakes in enemy nations. Some revived hollow earth myths and argued the drill was seeking an entrance to a hidden world populated by reptilian beings. Others connected it to the old Kola Sounds of Hell story and predicted something worse would emerge this time. On Chinese forums, some even claimed the government was searching for the legendary city of Shambhala, a mystical kingdom set in Tibetan tradition, to lie somewhere beneath the mountains of Asia. None of it has any connection to reality. But it reveals something powerful. The idea of going deep into the earth attracts the human imagination almost as strongly as going into space. What lies below us can feel just as mysterious as what lies above us. Reality is less theatrical, but far more impressive. Because the true challenges of ultra-deep drilling are brutal enough without myths. At 10 kilometers down, rock temperatures can rise beyond 200 degrees Celsius. Ordinary steel weakens. Electronics fail. Drilling mud, the engineered fluid used to cool the bit and carry crushed rock upward, begins to chemically degrade. Everything humans normally rely on starts breaking apart. Pressure is another enemy. Reservoir pressure at those depths can exceed 130 megapascals, roughly 1,300 atmospheres. If a crack opens in the well wall, superheated fluid or gas can explode upward like artillery fire, destroying equipment and killing crews. In the oil industry, this nightmare is known as a blowout. One of the most infamous examples was the Deepwater Horizon oil spill in the Gulf of Mexico, where a blowout killed 11 people and caused one of the worst marine oil spills in history. That happened offshore, not 10 kilometers beneath a desert. The risks at extreme depth are no small matter. Yet the greatest challenge is neither heat nor pressure. It is geometry. At 10 kilometers, the borehole diameter may narrow to around 20 to 22 centimeters, barely wider than a dinner plate. Meanwhile, the drill string hanging from the surface can weigh hundreds of tons. Steering a drill bit at the end of that suspended column is like carving a precise pattern at the bottom of a well using a 10-kilometer steel needle. A tiny vibration can jam the pipe. A slight deviation can trap the tool. That is exactly what happened at Kola in 1984, when 5 kilometers of pipe were lost forever underground. China studied those failures carefully. Its automated systems track bit position with near-millimeter precision, adjusting direction continuously without waiting for human reaction time. Even so, the final 910 meters of Shendi Take 1 consumed nearly 300 days, almost as long as the first 10,000 meters combined. The deeper you go, the harder every meter becomes. Earth does not surrender depth willingly. There is another side to this story that matters far beyond China. We live on this planet, yet we know less about its interior than we know about the surface of Mars. That sounds exaggerated, but it is not. We possess detailed maps of Martian terrain with meter-level resolution captured by orbiters. But maps of Earth 10 kilometers below our feet are often blurry approximations built from indirect signals. Every ultra-deep borehole becomes a rare window into the unknown, and nearly every time we open that window, reality contradicts expectations. Kola failed to find the basalt layer scientists were sure existed. A German well in Bavaria drilled to 9 kilometers discovered hot saline fluids few expected. Again and again, deeper exploration reveals surprises. Shendi, Take One, appears to be no exception. Early indications suggest parts of the Tarim Basin at extreme depth are structured differently than models predicted. There are also signs of real hydrocarbon potential. But China did not stop with one hole. Alongside Shendi, Take One, another major project began in July 2023 in Sichuan province. Shendi Chuanke 1, planned for similar depths with a focus on ultra-deep natural gas. Estimates suggest billions of cubic meters may be recoverable. Across the Tarim Basin, dozens of other deep wells are also operating, each adding new information about crustal structure and buried resources. China is not drilling a single hole. It is building a network of underground observatories. Over time, that network could evolve into a lithosphere monitoring system with few global rivals. And that brings us back to the question we began with. Why drill the deepest hole in Asia? Because it serves many goals at once. Oil and gas to reduce import dependence, geothermal energy to power growth with lower emissions, scientific data to understand the planet, seismic monitoring to help save lives, and prestige, to show the world that China can execute projects once associated only with Cold War superpowers. Any one of those reasons could justify a project of this scale. Together, they become something much larger. But there is one final reason, and it may be the most important of all. Ultra-deep drilling in the 21st century could become what spaceflight was in the 20th. Whoever masters depth may help control the next age of resources. Beneath the surface lie oil, gas, geothermal heat, strategic minerals, underground water, and materials still poorly understood. At several kilometers down, there may be reserves capable of sustaining industrial civilization for generations. Accessing them safely and efficiently could reshape economics, energy security, and geopolitics. The Kola Superdeep, well-discovered mineral-rich zones at extreme depth, including gold concentrations high enough to capture global attention. What China may uncover in the Tarim Basin remains unknown, but every core sample raised from below is a possible scientific breakthrough, or an economic one, sometimes both at once. Today, the Kola borehole on the Kola Peninsula stands abandoned. The drilling rig was dismantled. Buildings decayed. The shaft itself was sealed beneath a metal cap bolted shut. One of the Soviet Union's most ambitious scientific projects ended as silent ruins in the tundra. It is a striking symbol of an empire that collapsed before finishing what it began. Yet the data collected there never died. Kola's results are still cited in scientific papers across the world. The site fell quiet, but the knowledge survived. China understands that lesson. It is not merely repeating the Soviet experiment, it is extending it with tools the earlier generation never possessed. Automated rigs, new alloys that tolerate 200 degrees Celsius heat, real-time sensors, artificial intelligence systems that help control trajectory and vibration. These are advantages Soviet drillers could scarcely imagine. Technology has changed. The rocks below have not. Time will decide whether China can surpass the Kola record or eventually touch the mantle itself. But even if it stops at 11 kilometers, the achievement already matters. It is another opening into a world humans still barely know. We began in the Taklamakan Desert and traveled back to the frozen north of Russia. We moved from giant drilling towers to legends of screams from hell, from buried oil to the hidden architecture of the crust. And the deepest lesson of this story is surprisingly simple. We live on a planet we do not truly understand. We build artificial intelligence, edit genes, and explore the solar system. Yet we still struggle to drill more than 12 kilometers into the rock directly beneath our feet. That should humble us. Every ultra-deep borehole is a reminder that the greatest unknown may not be in distant galaxies, but below the ground we walk on every day. Each meter downward brings answers, and new questions. Questions humanity has asked since the first person looked not at the stars above, but at the earth below, and wondered what was hidden there. Will China break the Kola record? Will future drills reach the mantle? Or will the planet surprise us again, as it always seems to do? Write your thoughts in the comments and don't forget to subscribe. More stories are coming about how science keeps pushing the limits of what humans believe is possible. Until next time.